Okay, so this is our last case, initial value problem with complex roots. Again, write down the R equation. This time we need to use the quadratic formula. 2a minus b plus minus square root of 4 minus 4ac, which is 4 times 5, 20. So that's negative 16. So how do you think about the square root of negative 16? It's gonna be, since it's a negative, so once you take the square root, you should have an I in it. And then you 16 square root is just 4, so 4 times I. So that's gonna be 1 plus minus 2I. So that's our two roots. They are complex conjugates to each other. So how do you write down the general solution in this case? So we know that general solution, it's gonna be like a linear combination of e to the root times t. But then when we're in the complex roots case, we know e to some. We learned about the Euler's formula, right? So e to the I times something should be related to cosine and sine. So that's why the general solution for this case will look something like this. So it's e to the t cosine 2t plus c2 e to the t sine 2t. So if you think about it, what you're doing is, for this real part, it goes here, and then for the imaginary part, just the positive one. Put the imaginary part, the positive one, here, as the coefficient inside cosine and sine. So that's we're kind of at this point, we're just memorizing this. We're not deriving anything. So, and then to solve them, we plug in t equals 0, the whole thing is 1. So t equals 0, we get c1, this is 1. Cosine 0 is 1. And then this is c2, e to the 0 is 1. And then sine of 0 is 0. So that term goes away. So it's going to be 1. And then 1 prime. So let me kind of draw an arrow. So y prime, it's going to be, well, this time it's going to be a little kind of trouble to take the derivative because you need to use a product rule twice. But let's do that. So you have e to the t cosine t, and then negative 2 sine 2t, right? So remember, this 2 comes from taking derivative of the cosine 2t, because by chain rule, you need to multiply by this extra 2. And the derivative of cosine is negative sine. So be careful with that. So that's gonna be the derivative of the first term. Derivative of the second term is e to the t sine 2t, and then cosine 2t times 2. Okay, so I think that's correct. Let me know if I made any sign mistake, but I think that's correct. So now you can use the second condition. So plug in t equals 0 here, and again, be careful, e to the 0 is 1. And then what else? Like sine 0 is 0. Cosine 0 is 1. So these three things will kind of help you. So plug in 0, that's C1 let's do this. So that's a 1, that's 0. So I shouldn't, and then you have C2, this is 0, this is 2. Okay, so these two parentheses kind of matches these two parentheses. That's equal to -1. So then we know C1 is, well, it's already kind of solved, 1. C2 is going to be -1. Yes, so the final step is to make a conclusion now that we know C1 and C2. So it's e to the t cosine 2t negative e to the t sine 2t. Okay, so that's the solution. But so just to kind of recap, I think the most important thing is once you get the two complex conjugates, two complex roots, you separate them as the real part and the imaginary part. And for the imaginary part, kind of just use the positive value, put it inside as the coefficient inside the cosine sine. And this real part 1 goes to the exponent as usual. And the way to memorize that you have cosine and sine is to kind of, remember that we have the Euler's formula. E to the I theta is equal to cosine plus I sine, right? So that's how you, well, it's not, you need more like details to derive this, but then you kind of, the way to memorize that there are, extra stuff, cosine, sine, in this case with complex roots, is to kind of think of the Euler's formula. Whenever you have an I in the exponent, you should have something like cosine and sine.